Today I'm going to look at this. This is an analog to digital converter, the Texas Instruments ADS1015. You'll see that this particular board, it says ADS1115/1015. So this same board is obviously designed to support two different chips. So this chip actually is the 1015, which is a 12-bit A to D converter, and its bigger brother, the 1115, is 16-bit, so has 16 times more resolution. I'll talk a little bit more about resolution in a minute, but for now I just want to introduce the purpose of this. So I'm going to need to solder on a header so that we can experiment with this. You'll see on the back there you've got some silk screen that shows the various pins. So we've got SCL, SDA, which are for the I2C bus, so we're going to use I2C today. And there are four inputs here, A0 to A3, which because as you'll see, this chip has got a built-in multiplexer. So I'm going to experiment with this particular A to D converter today, because what I wanted to do is do some read some analog signals on the Raspberry Pi. Now the Raspberry Pi doesn't have any intrinsic A to D converter, so you always have to add something. And if you've seen any of my previous videos, I've used something called a PCF 8259, which is it's a much worse resolution A to D converter than this. The PCF chip is only 8 bits, so that one's particularly easy to use. This one with 12 bits resolution is quite nice, quite a good match for the capabilities of the Raspberry Pi, and can also provide at least 128 samples per second, which is quite fast. So if you want to read analog signals on the Raspberry Pi, then you do need to add on an A to D converter. If you're using the Arduino, then the Arduino has A to D converters built in that case 10-bit A to D converters, so there's no need to add any hardware on. But often it's really convenient to use the Raspberry Pi, and it means that you can write software in Python that can integrate to a variety of different analog sources like sensors. And I'll dig something out that we can use, maybe LDR for light measurement. Well, I'll see what I've got in the way of analog sensors. So let me just solder this up and we can start experimenting with the Pi. Let's just have a quick look at the datasheet for the ADS1015, because there's quite a nice block diagram here that shows the internals. So you can see on this side we've got the four inputs, A in 0 to 3. Over this side you've got the I2C interface, the alert ready pin, which I'll talk a little bit about in a minute. And in terms of building blocks of the A to D converter itself, so you've got the 12-bit ADC here in the center. This here is a programmable amplifier that you can use to change the gain, so you can change the sensitivity of the A to D converter. And then this is quite interesting here. So the reason that it has these four inputs is because although there's four inputs, but there's only one A to D converter. So this is a multiplexer, or MUX I've got here, but this is a multiplexer. So one possible thing that you can do, actually what we're doing today, is if we close one of these switches in the mux and we've got A0 connected through the PGA into the A to D converter, so then we're just reading from this one port here. But having 4 ports allows us to actually connect 4 bits of equipment, and by changing the switch configuration we can take a reading of multiple voltage inputs. But another thing that's quite interesting is here you see so there's a switch here to pull down to ground. So if this pin is pulled down to ground, then you're comparing whatever's on this pin with 0, so you're getting an absolute reading. But if you open that switch, you can then have for example, A in 3. If you close this switch, you've got A in 3 on one pin, and you could have A in 0 on another pin. So you're actually subtracting one from the other, and you're taking a differential reading. So you know, there's a lot of really clever stuff that you can do with the ADS1015 over and above just simply reading an analog value. So I've connected up the ADS1015 here. So rather than show you how these are plugged in detail, I'll show you a picture in a moment of how I interconnected these. It'll be clearer than trying to show you the wires here, I think. Now, an interesting thing, so if we look at the Raspberry Pi screen here, the Raspberry Pi now has this useful command. If you type in pinout, it actually it prints out what kind of board you've got. So here we're using the Raspberry Pi 0W, so it shows you what kind of processor it's got, and you know what kind of network it has, which is quite nice. And then it shows you the connector. So when the board is this way up with the SD card at the top, the micro SD, so the pinout here is what you see on the screen. So that's quite useful, and it helps to get all of the wires located correctly when you're trying to connect something like this. So if we just do a quick check that it can see the board, so if we use the I2C detect, I've used this a few times before in previous videos. So there you can see that at port 48 we have an I2C device which is visible. So we do see something, so in a moment we'll run a script and we'll actually interrogate that port and try and read a value from it. So let's first have a look at how I've interconnected the wires, and I'll explain that address 48. So the board is wired up in this way. So we've basically got the 4 wires of the I2C, so the 3.3 volts and the ground, which are the power supply. And then I2C's got these 2 control lines, so SCL and SDA. So those are quite clearly marked on this ADS1015 board. So those connect as you see here. There's also this pin address, so ADDR, which is quite clever actually, because depending on which of these 4 pins you interconnect it to, it sets a different I2C address for the board. So you see I've got a note here, so because I've tied ADDR to ground, it should have an I2C address of 48 hexadecimal, which is 72 in decimal. The other lines that are exposed on this board are of course the inputs. So we've got A0 to A3 as they're marked on this particular board, but if you look in the data sheet it calls these AN0 to AN3, so I'll just put both nomenclatures there so that you can see the correspondence. There's also this pin alert ready, which has a couple of different functions depending on how you program the chip. So one of the things that you can do with this, for example, is you can get it to set this pin high when the A to D conversion has happened. But I'm not going to use this particular pin today, so I might leave that for another day. So there, with that address pin pulled down to ground, so we're looking at I2C address 48. And if I have a if I just show you this script that I'm going to run, so so what we've got here, in fact, if I just load this, let's load it into the editor. Okay, so I've got a few libraries that I'm installing here. So these first two are ones that I've shown on my channel before. They're just a convenient way of talking to the I2C bus. But today I'm using this Adafruit provided library, which is specifically for the ADS1015 or 1115. So you see here I'm doing a bit of initialization. So first of all, creating an I2C object. This actually calls ADS1015, so this is saying that I've got a 1015 A to D converter connected to the I2C bus, and so I'm creating an object ADS to represent that. And then finally, Chan here is going to represent the chip, and it offers some abstraction so that I can quite easily use the values coming back from it. So here, if you look at what I'm printing out here, we've got chan.value. So this is literally the value, the binary value that's being read from the I2C bus. And then you can also do chan.voltage. That does a little bit of conversion under the covers, because it knows that it's a 3.3 volt interface on the Raspberry Pi, and so it does some conversion. It will actually return the real voltage. So if we have a look at what that looks like, if I run my script now, so it prints out two values here. So if you notice, I've actually got my A0 pin here is connected to this here, which is the ground wire. So this should be reading back 0 because everything has been grounded. So we see the value is 0, and then in turn the return voltage is also 0. Now if I allow that to float, so if you allow a MOS gate to float, there'll be a voltage that I can pick up on this pin. So let's have a look at that. So we'll run read AD again. And this time, so it's now reading a value of 5232, and then it converts that into the real voltage. So it can see a 0.81 volt reading on that pin. And if I actually hold on to the pin, it will read even higher. So if I do that, so that's now saying 27152. That's actually flipped to a negative voltage now. That's interesting, because it seems to have read so high that it's gone over into a negative number because of the 2's complement system, I guess. What we could do, because I've found a sensor that we can use. So this is actually a silicon solar cell that came from a garden light that I tore down. So this should produce about 2 volts, something like that. So if I get the multimeter out, let's just put that on the voltage setting. And if I'm not sure which pin is which, but let's just connect that. Oh, I've actually got that the wrong way around. So the white is the positive here. So there we go, it's reading about 2 volts. Now if I cover it up, the voltage drops right down, so we've got 1.3 something. And if I increase the illumination, so it's about 2.3 volts now. So that's quite a useful range. That won't overwhelm the A to D converter. So if we I'll just find some crop clips. So I just connect this one into ground. Connect that to the black, and I've got a red one which will be my signal wire, like so. And once again we'll do a read. So that's quite nice. So now we're getting that value 16144, and when it converts that into a voltage, it's just over 2 volts. And similarly, if I make it dark with my hand, let's run that again. So now the voltage has dropped down to 1.08 volts, or I could illuminate it even more, and now the voltage has gone up to 2.3 volts. So this ADS1015's, you know, quite a nice A to D converter because it's got good precision, but it's relatively easy to use as well, especially with that Adafruit library, which just kind of does all the hard work for you. So I promised I'd say something about the precision of A to D converters, so let me just quickly show you that. So to talk a little bit about the A to D converter resolution, so the PCF8259 that I mentioned, which is quite a humble device, so this has got 8-bit resolution, so 2 to the power 8 gives you 256 as the range, the resolution. So if for example you have a 5-volt interface, so 5 divided by 256 gives you the step size. So here 5 divided by 256 would give you about 20 millivolts. So with a 5-volt range, you've only got steps of 20 millivolts, which if you wanted to do something like have a voltmeter, build your own voltmeter, then 20 millivolts is quite a big jump, and it's not a very precise device. But the 8259 is quite good for things like connecting to an LDR, because if you just want to know whether the light reading is dark or light or somewhere in the middle, then you don't need much resolution, and so the 8259 is quite a nice inexpensive chip for that. The Arduinos have got a 10-bit resolution built in, so that gives you a range up to 1023, so 10 bits is 2 to the power 10, so you get the 1024 range, which is not bad, and a whole range of sensors work very well on the Arduino. The one we're looking at today, the ADS1015, is a more sophisticated device and it's got 12-bit resolution. So with two more bits than the Arduino, actually gives you 4 times the resolution. So instead of 1024 as your range, you've now got 4096. So you can see that as you add more bits, you're adding quite a lot more capability. And then the ADS1115, which is like the bigger brother for the 1015, goes up to 16 bits. So you can see again, you've got another another 4 bits gives you 16 times the resolution of the cheaper chip. So I mean, which one you use depends very much on the application, but you can see there's a whole range of different capabilities to choose from. So that's a basic, simple introduction to this this particular device. My test script I'll put on my GitHub site as usual, so that you can also use it, and I'll also put a link to the Adafruit library, which makes this experimentation so very easy. So thanks for watching. See you in the next video.